Well, looking back at the lectures we've done so far, we had one entitled Toward Common Filters, where we kind of compared the previous filters and decided to launch out in a new direction. Then we set up the common filter, gave a few examples. Then we talked about notation. We're 3 lectures into it, and we haven't even started developing the common filter. So now this is where the rubber hits the road. Given an estimate at time n-1, given all the observations up to time n-1, and p at time n-1, given observations up to n-1. Remember that p is the error covariance matrix. When an observation becomes available, we want to find the unbiased estimate of x of n at time n, given all the observations up to time n. And we want to find it in such a way that it minimizes the trace of p n given n. So, as you may recall, the trace of p n given n is equal to the expected norm of the error squared. So we'll do this in 2 steps. The first is that given our previous estimate of our state, x, we want to estimate what the state is going to be this time. We call this our prediction step. And we're going to use our state transition equation. Now, one thing I've noticed is that some people kind of miss this fact, but this state transition equation is going to be slightly different than what we had before. This is going to be our estimate update and not the update of the actual state. What does that mean? Well, it looks very much like the state update that we had that encapsulated the physics of our situation, or whatever the setup might be, except that this time we're using x hat, and notably we don't explicitly add noise. So, since the noise is zero mean, and we know nothing about it other than that, and perhaps its variance, our best estimate of the noise would be 0. So, if we're trying to find our best estimate of our state prediction, adding the best estimate of the noise, which is 0, would make a lot of sense. Thus, noise is not included in the prediction step. So, prediction step is this. The second step is going to be it's going to occur once we get our observation y of n, and now that we have our updated x hat, and given observations up to time n-1, we want to find an updated estimate because now we have the observations up to time n. And this, of course, is our estimate of x of n. We sometimes call this the observation step or observation update. Step. Okay, let's dive in to our prediction step detail. As noted above, since our process noise is zero mean, our estimate is best accomplished by simply taking our previous estimate and applying the state update equation to it. That gives us a noise, or an error, I guess I should say, x of n minus x hat n given n minus 1. So, in anticipation of where this is going, it sometimes helps to know, we're trying to minimize, of course, the expected noise. And a lot of it is just pushing through, applying the equations that we know. But there are a few magic steps, if you will. That is, observing that some of the complex expressions we have, we know in terms of other terms. And so we're just going to proceed and watch how things fall out. So the first thing we want to do is, oops, that's a comma, go ahead and express everything in terms of previous quantities. If, for example, we have an estimate of the previous error, well, let's go ahead and try to express things in those terms. So we know that x of n, and I should put in our B matrix there. There we go. It's just equal to the previous x plus the process noise. And then we're going to subtract x hat, and we already know what that looks like. That's a of n times x hat n minus 1 given n minus 1. And the first obvious simplification is that we can factor out our a n given n minus 1. And we have essentially now our previous error. And then, of course, the process noise that we'll keep out there. So this quantity is just E n minus 1 given n minus 1. So now we have an update for our error from n minus 1 given n minus 1 to E of n given n minus 1. So we can now rewrite this in terms of the errors. The first observation that we're going to make is if x hat of n minus 1 given n minus 1 is unbiased. And what does it mean to be unbiased? It means that the expected value of our prediction minus the expected value of the actual state is going to be 0. In other words, if that's unbiased, then the expected value of E n minus 1 given n minus 1 is equal to 0. Doesn't mean we don't have error, and that error may have a lot of energy, but on average, we're okay. Well, if that's the case, then when we take the expectation of this entire expression, then we get that error of n given n minus 1 is also unbiased. W is 0 mean, so its expectation is 0. The expectation of n given n minus 1 is 0. And so the entire expression tells us that the expected value of E at time n equals 0. Okay, we wanted an unbiased estimator. So this, if we have an unbiased estimator, then this update step keeps it an unbiased estimator. Now, for reasons that will become soon apparent, it's also going to be really useful for us to have an update to our P matrix. So to get that, we have P n given n minus 1 is equal to, this is by definition, the expected value of E n given n minus 1. It's an outer product, so we get the transpose on the second term, because these are column vectors, like so. And we have an expression for this, so we can write it all out. And so we're transpose on that side, and we're done. Well, note that Wn is white. So that implies that the error at time n minus 1, given n minus 1, is uncorrelated with W of n. This is going to be a nice simplifying step. That's because W of n, or rather, the error is based on quantities that have not yet seen W of n. It's based on everything up to time n minus 1. So as a result, we can write this P at time n given n minus 1 is equal to our A matrix n minus 1 times our previous P times A transpose of n minus 1 plus QW So the P comes from, when we multiply this all out, we're going to have our expected value of E n given n minus 1 times E n minus 1 given n minus 1 transpose. I'm sorry, that's both of them are E of n minus 1 given n minus 1. Cross terms will be 0, and then we'll have the expected value of W times W transpose. So this equation actually has a name. It's It's called the Riccati equation. So, step 1 summary. We have this update here and that update. Step 2 is going to take longer, so I'm going to split this lecture into 2 lectures at this point, and we'll pick up in the next one with our observation update.